Quality and Performance, Part 1. This is an important topic because all firms have to deal with quality management. In this lesson, we will introduce what quality is, what quality management is about, what are the costs and benefits of quality. Then we'll study some approaches to quality management like TQM, Total Quality Management, Six Sigma. And then we'll talk about quality control. In Part 1, we will only study acceptance sampling, and then in Part 2, we will study statistical process control and the associated topic of process capability. So let's get started with the introduction. Quality is a term used by customers to describe their general satisfaction with a service or product. Although customers evaluate the product or service they receive, from an operations perspective, we should consider that as an evaluation of the processes that produce that good or service. Why? Because quality problems are often the result of errors in the process. So if we can remove the errors from the process, we will remove the issues in the product or service. A defect is any instance when a process fails to satisfy its customer. Okay. Now we should keep in mind that different customer segments may have different requirements. So something that is a defect for one customer may not be a defect for another customer. Think about traveling in an airline. Lack of appropriate legroom or comfort may be a defect for a first-class passenger, but lack of legroom or comfort will not be a defect for an economy class passenger. It's more of like what the economy class is. The other thing to keep in mind is that companies set expectations based on a promise to deliver. So a company may say our product has these features or has this capability, and then failing to meet that promise to the customer would be a defect. If a customer is being unreasonable, right, and is expecting something that we never promised, then that is technically a defect, but that is a defect in setting the right customer expectations. It is not a defect in the product or service. So just keep in mind, if a customer is unhappy, we do call it a defect. But if the customer is being unreasonable, it is a defect in our communicating the right expectations to the customer. And if it is, if the customer is right and it is a problem, we have not delivered what we said we would deliver, then it is a quality defect. Now, there are some costs associated with ensuring quality. The first type of costs are called prevention costs. So companies will incur some cost when they try to make sure that defects don't happen, right? You can think of these costs as doing a quality check, for example. So before you deliver a product to a customer, you check it to make sure it doesn't have a problem. That testing may cost you, some time, and you may have to pay someone to do the test. It may add to your labor cost, right? And so these are called prevention costs to prevent defects from reaching the customer or occurring in the first place. Appraisal costs occur when a company wants to keep track of the performance of their processes. So maybe they measure certain variables or output parameters, and they keep track of them to make sure the processes are working properly. Internal failure costs are costs resulting from defects that are discovered before the product reaches the customer. So let's say you're making a product and you find some defects. You may decide to fix those defects, or you may decide to scrap those pieces and just build new ones. So rework and scrap costs are called internal failure costs. There was a failure, there was a defect. The only difference is that it was discovered within the company and not by the customer. Internal failure costs tend to be less than external failure costs. Okay. External failure costs, as the name sounds, are when the defect is discovered by the customer, right, or after the customer receives the item or service. So in external failure costs, you may have to do a warranty. So you may have to take that defective piece back and ship the customer a perfectly fine good piece, or a customer may just return the item. There will be loss of goodwill, bad reputation, right? So the best thing is to prevent defects in the first place. Like that's where you want to be, right? Second, so that's like number one. You want to avoid defects. That's the best way to save money, to save costs, right? And prevention costs and appraisal costs kind of tend to go together. You're usually appraising the level of performance of your processes and trying to prevent defects. Okay, the second, well, if you're not able to prevent all the defects, at least you should hope that you can catch the defects internally. And then the third option is that the defects actually get shipped out, and that has the highest costs. Okay. Ethical failure costs are costs associated with defects, but the difference between these and external failure costs are that in this case, the defect was known to the company. So knowingly, the company passed that defect on to the customer. If you haven't worked in management for a long time, or you don't have a lot of experience with how companies work, you might think that can never happen. You know, why would a company ever ship something that they know to be defective? Unfortunately, it has happened many times and continues to happen. Okay, the classic example is Ford Pinto, which was a car which could blow up when hit from rear-ended, when hit from the back. And Ford, although Ford knew that problem, they still shipped out that car, and then people got into car fires when they were rear-ended on a road. You may have recently heard, a few years ago, heard about the Volkswagen emissions scandal. So Volkswagen had a program which detected when the car was being tested for emissions, was in an emissions test facility, and it ran the car differently from when the car was running on a road. So on the road, the Volkswagen car had higher emissions, but the car was still able to pass the test because the software in the car detected that the car was being tested, and it reduced its emissions just for the test, and then went back to having lots of emissions. Ethical failure costs can be huge. A company can damage their brand, and it may remain damaged for years. They may have fines to pay. So Volkswagen had, the cost was 30 billion. I'm not sure if this was the global cost or just the cost in the US. There may have been additional costs in Europe, for example, right? That was just the cost to fix the vehicles. And then part of their agreement, I believe, in the US was they invested in some electric charging stations, because electric vehicles have, no emissions, at least at the stage when the vehicle is being used. The production of electricity may have had emissions. And so they had to do a lot of stuff. You can read about it online. There have been cases where lead was found in toys, and then when the companies were caught for not being serious about keeping harmful metals away from toys, they had to do recalls and so forth. It can take a long time to heal from a bad reputation. So unknowingly shipping out defects can have huge costs. Now, we saw that having bad quality has costs, internal failure costs, external failure costs, ethical costs, right? We also saw that avoiding defects have costs, like appraisal costs, prevention costs. So which costs are lower? Is it better to prevent defects or just pay the cost if you're caught? Well, the benefits of superior quality are so large that it's almost always better to just have some preventive costs and appraisal costs and just avoid defects. Okay. Why? Because if you have high quality, which means if you have lack of defects, if there's a lack of defects, that's what we mean by quality. Here we're talking about conformance quality right now, right? Conformance quality, not talking about product features, although that is part of quality as well, right? So if you remember our discussion of competitive priorities, we talked about quality having multiple dimensions, two of which were performance and conformance. So if you don't have defects, we have enhanced reputation for quality. Think companies like Toyota, Sony, right? These companies, I guess, I don't know, perhaps Dell, maybe Apple for sure, right? These companies are known for quality, and so sometimes they're able to charge a premium for their product or sell a lot of product to get volumes, right? And so this can lead to that and that, right? Increased market share, ability to charge premium prices. Greater customer loyalty. So if customers find something to be of high quality, they tend to stick to it, right? They have lower costs of failure, like lower liability costs. Also lower production costs because there's no rework and no scrap, right? No rework, no scrap. You do things right the first time, that's lower your production costs. Because remember, you might remember that from the competitive priorities discussion, that conformance quality, if it goes up, if you have less defects, your manufacturing costs go down, right? Unlike performance quality, if you add more features to the product or use premium materials to increase your performance quality, your cost tends to go up with performance quality. But conformance quality is the reverse. As you have higher conformance, you have no defects, your production costs will go down. So that's an advantage of conformance quality. Okay. There are fewer service or production disruptions. So there's you don't have disruptions on the factory floor because you ran into a defect and you have to redo stuff. And higher profits. Right, so all of this, less costs, higher market share, all of this leads to, that's the end result, gives you more profits, especially in the long run. History of quality management. This part of the lesson on the history of quality management is not, is optional. Right, so you can skip ahead if you don't want to learn some of the history. I like to share it because I think it's interesting and there are some lessons to be drawn from it, some insights to be learned. But it's not something that you'll see being tested or on the homework. It's just FYI for your information. So concern about quality is nothing new. We can find references to quality 2000 to 3000 BC or before the Common Era. In Babylonia, which is modern day Iraq, we find a reference in the Code of Hammurabi to this rule or law. The mason who builds a house which falls down and kills the inmate shall be put to death. So the cost of a quality defect or a serious defect at the time was death. For when pyramids of Egypt were built, processes for how to quarry and dress the stones and have the stones ready to be used were kind of standardized so that all this, the stones had a high degree of standardization, which enabled them to build the pyramid accurately, right? So that was an early form of quality control. Then in the 13th to 19th century, quality management became built into guilds. So guilds were groups of craftsmen, right? And what they would do is they would say, we have our standards for quality, and the members must follow these best practices and standards, so that if any customer buys a product which is made by a member of our guilds, that customer can expect a certain level of quality, right? And to indicate, this is an early form of branding, to indicate or build brand strength with the customer. They would put a mark for their guilds, and sometimes a mark representing the craftsman as well, right? Such marks were useful for tracing defective products back to which craftsman built them. So if there was a defect, the customer could go to the guild and they would have the craftsman fix it. And they also became brands or symbols to designate quality and reputation of the craftsman. So that was another early form of quality management. In the 19th century, with the Industrial Revolution, manufacturing replaced the craftsmanship model. So young people learned a skilled trade by being apprentice to a master. Goods mostly sold locally, and craftsmen had personal stake in quality, because if their quality was low, people wouldn't come to them. Okay, so that was the apprenticeship, that serving under a master until you produce your masterpiece, which allowed you to become a master. That was the craftsmanship model, and that was replaced by factories after the Industrial Revolution. So with factories, quality was ensured through the skill of the workers, as before, as with craftsmen. But because of processes, you didn't need every single worker to be highly skilled. You could have some skilled workers and some not so skilled, because you wouldn't need a person to build the whole item. So if you are building a piece of furniture, right, in a craftsman model, the craftsman might build the entire furniture. In this model, the craftsman might do the complicated stuff, and then some other workers would do some of the easier steps. And then there was obviously inspections in factories to find defects and fix them before they got shipped out. Then in the 19th century, we also had the rise of what's sometimes called scientific management, okay, or Taylorism. This was the idea that managers should collect data and design processes that ensure quality and efficiency. So focus on productivity and specialization of labor, time and motion studies, where manufacturing a good was split into small, tiny tasks, and then data was collected on how long it takes to do each task, what is the best way to do it. So basically, the manufacturing process, M&F process, was standardized in terms of the work involved, right? And each step of the process was relatively easy to do, so you could get workers to do it. Inspectors were there to deal with quality control, right? And if a defect was found, if a defect was shipped out, the concern was, why did it not get caught in inspection? That was the idea, okay, that there are going to be some defects and inspection should catch them. Now, World War II, I'm sure you might be familiar with the history of World War II. When the U.S. entered World War II, there was a huge need for production of war equipment and arms to support the Allies. Obviously, safety was a key issue, right? Because if your weapons fail on the battlefield, it could mean the death of a soldier. And so The army inspected almost every item before sending it for use initially. Later, they adopted sampling techniques, which are called acceptance sampling, how much to sample and so forth. The army got help from statisticians, and so Shewhart's statistical process control approach started to be used in the manufacturing of arms. Okay. Top priority for the firms was meeting production deadlines, just because there was such a big need for the military hardware. However, to ensure quality, they did use sampling techniques as well as some statistical process control that you will learn later in this quality management lecture or the next part of it. After the war effort, most such statistics-based quality control tools like sampling techniques or especially process control were terminated. Why? Because companies were trying to produce a lot to meet the post-war demand as Europe was being rebuilt and so forth. And so the goal was to capture market share by pushing out a lot of volume. So the goal was to produce in volumes, and quality was a secondary concern. Now, as you might already know, Japan was quite devastated in World War II. And so when the Japanese wanted to rebuild their country, rebuild the economy, they formed a union of Japanese scientists and engineers to help out. Okay. At the time, Japan did not have a reputation for quality. So Japanese products were considered to be low quality. US was concerned with quantity, not quality, right? To meet the post-World War II demand and reconstruction needs. And so people who had pioneered how to ensure quality during the World War II effort, who popularized statistical process control and so forth, they were feeling ignored in the US. So Edward Deming, Joseph Juran, right? They had developed on Shewhart's work on statistical process control, and they had very good ideas on how to ensure quality, but they were unable to find a receptive audience in the US. So who was Edward Deming? So Edward Deming and Joseph Juran are two pioneers of quality management. Edward Deming was a mathematical physicist. His 14 management principles became very famous. He was an advocate of statistical process control and emphasized continuous improvement. Okay, so this is what kind of look like. And you'll see his picture crop up a lot of times in my quality management lectures, because I often use quotes by him, or the way he used to teach quality management. I use some of the techniques he used to use in this lesson. Joseph Juran was an engineer. This is a picture of one of his books, and his popular book was Juran's Quality Handbook. So he also had good ideas extending the work of Shewhart. Deming found a receptive audience willing to try his methods in Japan. Okay. Deming said that he told Japanese industrialists that their quality could be the best in the world instead of the worst. Many were skeptical because these methods were new. Businessmen didn't have experience with these methods. That's why in the US, a lot of people were not listening to these quality gurus either. And so Deming says he was the only man in Japan who believed the Japanese industry could do that. Deming told the Japanese they would capture world markets in some industries like electronics, automotive, in 5 years if they followed his advice. And he says that they beat his prediction. It took them about 4 years to really improve their quality, be one of the best in the world. In recognition of Deming's efforts to help Japan, the Japanese, Society of Engineers created the Deming Prize, and he was also awarded the Second Order Medal of the sacred treasure by Emperor Hirohito. The Japanese were looking for knowledge on how to have high quality so they could, export products and improve their economy. And so they also invited Jurin to teach. Okay. Jurin had a strong reputation globally, and he was known to be one of the top quality gurus. So people were willing to listen to him in Japan. And you can think about the culture in Japan at the time. They were really focused on rebuilding the economy and producing quality products. Henry Ford's book on manufacturing became a bestseller in Japan. There were weekly radio programs that trained workers and supervisors and managers on statistics and Dr. Deming's methods. Right, so people would listen to those quality management talks in their homes on radio. And Dr. Deming and Jurin became celebrities in constant demand as speakers and consultants across Japan. So you can see that Japan is really warming up to try out these ideas of quality management, where where U.S. manufacturers are not that receptive at that time. The results started to show. Japanese industries began to take over world markets in certain industries. At one point, managers at Ford had joked that Honda could at best produce engines for lawnmowers because they felt that they don't have the technology, they can't produce a quality engine. And then we all know what happened with Toyota and Honda and other Japanese manufacturers. So could it have happened if the US gurus had not gone to Japan? Jurin believes it would have happened anyway. He believes that the Japanese would have discovered their ideas because they were really focused on quality, they were motivated, they were investing time and resources into it, but it would have taken them longer. With the help of these quality gurus, they were able to do it quickly. The Japanese also added to our knowledge of quality management. So you might have heard of TPS, the Toyota Production System, TPS. Another name is lean, or the lean methodology. So the Japanese built upon the works of Jurin and Deming and extended them to contribute to the knowledge and quality management, which the entire world benefits from. So the entire world benefits from Jurin, Deming, Schuhart, as well as the Japanese masters of quality who learned from these greats. By the 1960s, Jurin began to report to Americans on new ideas on quality coming out of Japan. So initially, ideas had gone from the US, which were developed during World War II, they'd gone to Japan. And now, with improvements and with new ideas are starting to flow from Japan to the US the other way, like quality circles. Initially, the US manufacturers thought that Japanese success was price related. They felt maybe things are cheap in Japan, they can build a quality product, their labor is cheaper, things like that. Because there was a strongly held belief in the US that high quality meant high cost, which is true for performance quality, because if you add more features, you use more expensive materials, that product is going to cost more. But it is not true for conformance quality. Removing defects reduces costs, right? And so people in the US kind of thought that higher quality, higher cost for all types of quality, although it is not true for conformance quality. So their initial reaction was the manufacturers tried to reduce domestic production costs, lobbied for import controls, quotas, and duties, so that the Japanese goods, which were of a higher quality and cheaper, would not take over US markets. The Japanese were able to create higher quality products at lower costs, right? Shattering the myth that high quality must mean high price. Here, obviously, we mean high conformance quality and not high performance quality. Okay, but still, initially people did not separate the two. People did not separate performance and conformance quality, and the discussion was often about quality in general, right? But basically, what's happening was Japanese had higher conformance quality, which reduced their costs. However, some CEOs were very brilliant. They saw what was happening, and they said we need to steer the US into the right direction. And so a lot of initiatives were started. The total quality management approach was popularized in the US in the 1980s to improve quality of US manufacturing. ISO 9000 standard was formed to encourage firms to adopt the standard to show that they had a quality management processes in place. The Baldrige National Quality Program and the Malcolm Baldrige National Quality Award were established by the US Congress to reward companies that had high quality. Just a summary on some of the main figures in quality management. If you want to read on them, read their biography or read classic books by them if you're interested in quality. So Shewhart was, very early on. Perhaps we can say the founder of statistical process control, right? And then Juran and Deming extended his ideas. And then Japanese who extended the work of Juran and Deming were Kaoru Ishikawa, Taguchi, Shigo Shingo, right? And then as Japanese ideas flowed back into the US, some US quality gurus picked up and added to the conversation, including Philip Crosby and Tom Peters. So a resource, a good summary of the history of quality management. You can read this resource and also read more about these people if you're interested. Okay, so that was the end of the history part, right? So that was optional. So now we're going to go and talk about TQM and Six Sigma, and this part is regular lecture. This is not optional. This is not FYI. So we need to know about TQM and Six Sigma in quality management. Okay, so you can't really improve quality just by pressurizing workers and telling them to do better, right? Deming found that 85% of the time the reasons for failure to meet customer expectations, i.e. reasons for defects, are deficiencies in processes and systems rather than the fault of the employee. So blaming employees and pressurizing them is not likely to yield good results. You have to find out where the problems are in the systems or the processes. Let's talk about TQM, Total Quality Management. It is a collection of ideas that can help companies improve their quality. The first major idea in TQM is that quality should be customer-centric. It should be defined from a customer's perspective. Oftentimes, engineers are writing product specifications. They might think that something is very important for quality. However, customers may not care about that thing. So the first idea in TQM is don't waste efforts on things the customer doesn't care about. Focus on things the customer cares about. So be customer focused in your quality definition, in your product design. Involve employees. Okay, quality is not the responsibility of some senior manager or operations manager. A manager cannot do everything by himself or herself. You need to involve employees at all levels in continuous improvement and quality management, and have the employees take ownership of quality. Okay. Six Sigma is another system. So TQM is more about you setting goals and having teams that work on quality improvement and things like that. Six Sigma is another approach to improving quality, and they're not mutually exclusive. You could do both. You could do both at the same time. Okay, they're not mutually exclusive in any way. Six Sigma's focus is on reducing variability in the system, because as you reduce variability, you can produce consistent, standardized output. And that reduces defects. Let's see some of the major ideas in TQM. So this is called the TQM wheel, and you can see at the very center is customer satisfaction. That's at the heart of TQM. Then the next two most important things that you need to do to get customer satisfaction is continuous improvement, always improving wherever you are, and employee involvement. And employee involvement drives continuous improvement, right? Because employees find ideas on how they can improve quality, and then they go ahead and implement them. Okay. And then on the outside ring, you have product design. You must design the product to meet customer specs and for quality. Purchasing must ensure quality inputs to the process, because if your components and raw materials are not high quality, you're not going to be able to produce high quality products. Benchmarking means comparing your quality level to your competitors, so you're always improving, you're always trying to stay ahead of the competition. And then you have to teach your workers some problem solving tools so that your workers and employees can get involved in this quality effort to improve quality. Right? Just like process design, product and service design, both of these things kind of go hand in hand, and you have to do both of them by keeping customer satisfaction in the mind. So the design of the service and the product must be driven by customer satisfaction concerns, and also the design of the process. If you do all of that, that is like implementing TQM in a company. Now, in TQM, what is customer satisfaction? Conformance to specific, well, it has, customer satisfaction, think of it like, you can think of it like quality, right? Because if the customer is satisfied, you have quality. So basically, we're saying what are the dimensions of quality. So you have conformance quality, like we talked about, right? And then we have performance quality, the features part, which give value, right? The higher the value means the higher the features, the more the customers are willing to pay. And then you can say maybe performance quality also is about fitness for use. Does it do what it's supposed to do? Does it have all the features it promises? If it's part of the specs, then maybe this is conformance quality, but it's kind of like a related idea. Okay, that does it meet specs? Okay, this is more in terms of specs, and this is more in terms of from a user perspective. So this is, does it meet the design specs? And fitness for use is more of like, is the user happy using the product, right? So fitness for use actually captures both performance and conformance quality. You have to have both for the user to like the product. Support, advertising, information, post-transactional elements like warranty, troubleshooting, returns, things like that. So providing support with your products and services. And psychological impressions, which is about aesthetics, how well does the product look and feel, and things like that. And there could be other dimensions. This is not an exhaustive list, right? Depending on your context, you might come up with other dimensions related to the product, which are important for customer satisfaction and hence part of quality. So anything that is important for customer satisfaction becomes a part of quality in TQM, Total Quality Management. Okay. Employee involvement has to do with execution. How do you improve your quality? Well, the best way is to have a culture of quality where within the organization, every process has customers. So you have internal customers. So purchasing has internal customers, which are people on the assembly line, which are going to assemble those components into the product. Because purchasing, the components it sources get used up by the next step, which is assembly, for example. Employees must treat internal customers just as seriously as external ones. Right, so this has to do with quality at source. Do it right the first time. Don't try to inspect quality into the product, but actually produce things which are defect-free. Employees take ownership of quality. Their role is not just to produce volume, but to produce things of the desired quality. You empower the employees, which means you give them decision-making ability to make small changes that can improve quality. Larger changes might have a chain of approval, things like that. Right? So you give people the tools, teach them how to improve quality, how to analyze problems, and then you let them go and do it. The surprising, well, or maybe not so surprising thing is that people do not like repetitive work. So working on quality improvement projects gives them more variety and leads to more worker satisfaction. They feel their voice is being heard and they're doing, more fulfilling work. So this actually, having a culture of quality and employee empowerment, this actually boosts employee morale. Okay. I do have some links to important videos in this lesson, so please do pause the video that you're watching, go to the slides and play these links, and then come back to continue. Continuous improvement means that you're always improving your quality. So there are various ways to do that. One is to have Kaizen events. Kai means change, Zen means good, so good change. Kaizen events are 1 day or weekend long events where you make small changes, so incremental improvements usually. So you kind of brainstorm with people, you get together on a weekend when or on a day when the production is not happening or it's happening at a low volume, and you go through quickly and you find small improvements you can make. So things you can just change in a day or two. Okay, taking small steps regularly adds up over time. That's the idea of Kaizen or continuous improvement. You want to use problem-solving tools like Six Sigma, TQM tools, lean methodologies. All of these methodologies have statistical tools, collecting data on quality problems, root cause analysis, Ishikawa diagram or fishbone diagram, all of those nice stuff you use, and you have to train the employees to use those tools. And then we often use the plan, do, study, act cycle, which is also called the Deming wheel, which means first, before, in Kaizen, you can make small changes immediately, but other than Kaizen, you want to make changes in a systematic way. So first you plan, document, and analyze current state. So it's okay, what is the current state of production? What is the defect rate? So forth. Then you implement some changes. Then you study whether the changes were good, whether we have met our goals of improvement, and if so, then you standardize that changed process. You say, okay, this is how we're going to do these things in the future because we are doing better with these changes. And then if the quality is still not up to par, you repeat the cycle. Okay, so this just means you do things in a standardized fashion. Okay, and you should know what each stage is. What is planning about, what is due about, what is a study about. Studies about verifying that the changes have happened and the plan has been met, the improvement goals have been met. Six Sigma is another methodology to improve quality, which if you think about TQM, what is TQM focusing on? TQM focuses on continuous improvement, right? Being customer centric, and employee involvement, things like that. Right? Those are the focus of TQM. So you can do TQM with Six Sigma as well. Six Sigma's focus is on reducing variation and hence reducing defect rates. Okay. So Deming also really placed a lot of importance on reducing variation. He said, if I had to reduce my message for management to just a few words, I would say it all had to do with reducing variation. So what is variation? Variation is when the same process produces something slightly different over time. So if you're making pizza, one pizza is 12 inches in diameter, the next one is 11.5, the next one is 12.2, the next one is 13. There's too much variation in the output. So you want to reduce that variation because that variation means there's a higher chance of defect if you have a lot of variation. This is a good video which is an introduction to Six Sigma. Kind of talks about a systematic way to collect data, do some root cause analysis, and improve the process. You can also call it TQM. The process used in this video applies to TQM as well. So again, I encourage you, pause the video, go to the slides, get the YouTube link, and play the video. I don't want to play videos within this recording because if I decide to host it on YouTube, if you have other YouTube videos in your YouTube video, YouTube could have copyright issues and so forth. So I'm just giving you the link. You need to pause this video and go and watch this video and then return to the lecture. Okay, so to understand process variability, I think this is a very nice diagram which explains what's happening. Okay, so this is the ideal because you want your process output to be on the money, to hit the target. Okay, so if you take an average of these x's, on average you're hitting the target, and you want your output to have low variation. All the x's are close to each other. They are not spread apart. if you have too much variation in the process, your output would look something like this, where your x's, or the points you actually hit, are too far apart, because there's a lot of variation between one output to the next output. Some pizzas are small, others are big. Okay, so that could be one problem, where you have to reduce the variation in the process to get to a picture like this. The other problem could be your process is not centered properly. So there's a bias in your process. So look at this picture right here. Our points are pretty close to each other, so we don't have variability, or too much variability. We have some variability, but on average, we are off center. So our average is not centered on the target value. So we need to do adjustments to our process so that we are around the center value, and we are closer to the target value. Six Sigma. So the sigma is a symbol for standard deviation, which tells you, Six Sigma is focused on reduction of standard deviation or variation. Six Sigma refers to there being 6 standard deviations between the average of a process and the specification limits. So for example, if you have, you're making a nut, okay, and the head is supposed to be 10 millimeters in diameters, okay, and let's say the specification says that it's okay if the head is between 9.5, or let's just make it simple, between 9 millimeter to 11 millimeter is okay. So you have some tolerance, right? You have some tolerance. But you should ideally be at 10, but if you go up to 11 or go down to 9, you're fine. So the specification limits would be 9 and 11 millimeters, the tolerance limits. And the idea is that your process to make this nut should be so accurate that you're almost always very close to 10, and you rarely get close to 9 and 11. Because if you draw your process's output, your process centered at 10 and it has some standard deviation, some nuts are a little bit less than 10, a little bit less, more than 10, but they almost never go to 11 millimeter or almost never go to 9 millimeter. They're always around 10. So that's the idea of Six Sigma, that your output is very precise and it doesn't go close to the specification limits. Because if you were to exceed the specification limit, go here or here, then you would have a defect. Okay, so what is, you might have heard, okay, about 6 Sigma, 3 Sigma, 4 Sigma, these Sigma levels. Excuse me. The Sigma levels are just, the Sigma levels explain how few defects you're going to have. The bigger the Sigma level, the fewer the defects you can have. So with 2 Sigma, per million opportunities, you'll have about 308,000 defects. With 3 Sigma, you'll have about 66,000, right, per million opportunities. If you make a million parts, about 66,000 could be out of the tolerance. 4 Sigma is going to be 6,000 only, 5 Sigma 233 over a million, and 6 Sigma is only 3.4 parts per million are going to have a defect. 3.8 Sigma is sometimes considered good enough, and it corresponds to 99% good pieces, only a 1% defect rate. However, this can be too high. In many situations, 1% is too high of a defect rate. Imagine a surgery procedure where 1% of the patients die. Well, that's a lot of deaths being caused by that procedure, because thousands of people may get that surgery. So depending on the context, 1% may not be good enough. So 3.8 or 4 Sigma level may not be good enough, and you may have to go up to 6 Sigma or beyond. Let's do a comparison between 3.8 Sigma, which is 99% good, because if you went to somebody and said, my quality is 99% of the time I'm producing the things within specs, people might think, well, that's really good, because 99% sounds like a very high percentage. But let's see what happens with 99%, which is 3.8 sigma level versus a 6 sigma level quality. If the post office operated at a 3.8 sigma level, they would lose 20,000 pieces of mail every single hour. At 6 sigma level, they will only lose 7 pieces of mail per hour. If you had your water supply at a 3.8 sigma level, you would have unsafe drinking water for 15 minutes every day. With 6 sigma, it's 1 unsafe minute every 7 months. 5,000 incorrect surgical operations per week in the US, given the average amount of surgeries that happen, or 1.7 incorrect operations per week. 2 incorrect landings at most major airports every day at 3.8 sigma level for the aircraft, flying the aircraft. 1 short or long landing every 5 years at 6 sigma level. So you can see how your safety is really at 6 sigma. Here you're living in a dangerous type of situation where the defects are really unacceptable levels in many situations. If the pharmacies work at 3.8 sigma, they're going to give out 200,000 wrong drug prescriptions versus 68 wrong prescriptions per year in the US. These are all stats about the US. No electricity for almost 7 hours each month at 3.8 sigma level of power supply. 1 hour without electricity every 34 years at 6 sigma level power supply. So you can see for our power supply, for our healthcare, for water, for air travel, for post office, we really want 6 sigma or more or a higher level of quality where defects are really, really rare. The pioneers of 6 sigma were General Electric and Motorola, and they got a lot of benefit from it. Jack Welch said that 6 sigma will bring GE to a whole new level of quality. He made 6 sigma training compulsory for every employee at GE. GE was able to save $2 billion in a 5-year span of implementing 6 sigma. Okay, so that's $2 billion straight to their bottom line. And then, after another year or so, they had saved up to $5 billion. Okay. In Motorola, example is similar. They saved $2.2 billion over a 4-year time frame from 6 sigma. And they said that if we can't express what we know in the form of numbers, we really don't know much about it. If you don't know much about it, we cannot control it. If you cannot control it, we're at the mercy of chance. So you have to find numerical measures of quality. For example, the size of the product, right? Size can be a numerical measurement: length, width, height, weight, right? Length, width, height, weight, right? Concentration of a particular compound in your product, things like that. So you can find numerical measures which are associated with quality, and then you can use 6 sigma to reduce the variation on the numerical measures, so they're always at the target values, and that reduces variation and defects. This is a really powerful example of applying 6 sigma and 2 km principles to a kitchen, like just a kitchen in your home. And you can see the drastic improvements you can get with just a few minutes of brainstorming using these sorts of techniques. So I highly encourage you to watch this video. Pause the current lecture video, go to the lecture slides, copy paste the link, watch the video linked here, and then return to this lecture. So now that we've talked about what is quality, the costs associated with quality, we've talked about 2 approaches to quality management, TQM and 6 sigma, broadly. Now we're going to get into the topic of quality control. And in this part of the lecture, we're only going to touch acceptance sampling, and the next part of the lecture we'll talk about process capability and statistical process control. So in general, there are 2 approaches to quality. One is called an inspection-based approach, right, which is that you produce something and you inspect it before shipping it out, so that the quality errors have internal quality cost and not external quality cost, you can fix the errors before you ship it out. And this is what was also used in World War II, where if you're, especially if you're this is often used when you're producing in batches or receiving product from supplier in batches. So you take a whole batch and you randomly sample, maybe you take, I don't know, 20 units out of it and you test them. And, you know, if more than 5 are bad or more than 3 are bad, you have some threshold. If more than that number are bad, then you reject the whole batch and you say, okay, this batch has a problem. You investigate it and fix it before this batch can be shipped out. If less than the threshold are bad, then you say, okay, there's only a few bad apples. I'm going to ship out the batch. It's mostly okay. Okay. Process control is about ensuring that a process is in control. What does in control mean? We're going to talk all about that in part 2 of the lecture, so it will make more sense then. But this is a different approach to quality management, where you just ensure that the process is working as it should. And if the process is working as it should, then you should not have defects. Your output should be high quality, right? So this is more inspection. This is more ensuring the process works as desired. So let's talk about acceptance sampling. It's the application of statistical techniques, because, you know, statistics tells you how big a sample to take, what the threshold should be, things like that, right? And then you have an acceptable quality level. What is the quality level acceptable to the customer? Because the assumption is you're not going to have 0 defects. You're going to have some low level of defects. So what defect rate will the customer put up with? Right? If the customer will put up with a high defect rate, you have to sample very little. But if the customer is very picky and they'll only accept a very, very low defect rate, then you have to sample more to make sure the batches you send out or the product you send out has no errors or very few errors. So how does this work? You inspect a sample of the product to infer about the quality of a whole batch, as it is usually too costly to inspect every single unit. If the sample has more defects than a max threshold level, then the entire batch is rejected and we do not ship it out or pass it on to the next customer. If the sample has less defects than a certain lower threshold, then the entire batch is accepted, because we're saying the defect rate is too low. You know, we have to accept certain small level of defects. And if your defects turn out to be between the max threshold and the lower threshold, then a second sample may be taken to figure out where this should go. You're kind of like on the fence at that stage, and you might take a second sample to decide whether to send the batch back for reprocessing or to ship it out. Sometimes if you are within the 2 levels between the max and the lower threshold, the entire batch is inspected and defective items returned. Or the entire batch is returned. So you don't take a second sample. Sometimes you just go with the information you got, and then you either inspect the whole batch or and use what you can, or you reject the whole batch. What should be your sample size? What is that maximum threshold? What is that lower threshold? These are all numbers we can calculate using statistics. We don't do it in this lecture, but if you're interested, you can find information in quality management textbooks or online, or you can find acceptance sampling research papers that show you exactly how to find these levels. There are software which can do that for you as well. So if you know that, okay, my defect rate must be below 1% or 0.1%, you can set that, you can give it some past data, and the software can calculate these for you. What is good about acceptance sampling is that it's usually it's easy to set up. It's easy to set up because all you're doing is inspection with some rules, right? And if the sample size is not too high, if the sample size is small, then the cost is low to set it up, right? Because the cost of acceptance sampling goes up if you sample more and more product. So if it's easy to set up and if the sample size is reasonable, you're going to have low cost, right? That's the advantage. What are the disadvantages? It is still more costly than building quality into the process, because doing it right the first time is the cheapest way to do it. Even if this acceptance sampling catches some errors, you still have to do rework or repair those items or scrap them, versus if you just produce right the first time which is the idea of Six Sigma, reduce process variability. So you're always producing things which are within spec. You never have defects in the first place. So acceptance sampling, it may not be that expensive, but it's still probably going to cost more than building quality into the process so you produce right the first time. Produce right the first time is often like the best approach. And then this is the second one, is the major problem I have, which I feel is more important with acceptance sampling. It doesn't scale well as your quality improve, because as you improve your quality, your defect rate falls. The lower the defect rate, the bigger the sample size you need to be able to catch any defects with acceptance sampling. So if your defect rate is like 0.01%, you're going to need a bigger sample from the batch to figure out whether this batch is is defective or not defective overall, right? So you have to take a bigger sample the lower the defect rate, which kind of defeats the purpose. So as your defect rate falls, right, you're getting happier, your defect rate is falling, you have less cost now, you're not having a lot of scrap or rework. Well, it turns out you have to take bigger and bigger sample sizes to be able to check for quality with acceptance sampling, and the bigger sample sizes increase your quality assurance costs, right? And so they take away some of the advantage of higher quality. At some point, at some low defect rate, acceptance sampling becomes too costly. So when defect rates are really low, you can't really use acceptance sampling. It is less reliable than building quality into the process, because you're playing the game of chance. Even if you calculate the sample size properly and so forth, there's still a small chance that some batches may go through which have high defect rates. So your customer satisfaction, especially in a business-to-business context, if you're shipping parts to a large manufacturer, your customer satisfaction can suffer if some batches get through which have a high number of defects. When should you inspect? When it is reasonable to use acceptance sampling? If you're purchasing raw materials or components from a supplier, and the supplier has a policy where you can only return items within 30 days, otherwise they will not trust your explanation. They'll think you caused the problem. So in that case, you want to inspect the items as they arrive, because if a lot of items are bad, maybe you want to send them back before the 30 days are up, right? Things like that. If you have major phases of production, it might make sense to do some sort of an inspection after every phase, so that you don't start the next phase and do a ton of expensive work on the product before you have really determined that the product is defect free. You may do inspection at critical control points. Okay. So in a food plant, for example, critical control points are points or in the process where pollution is likely to occur. So maybe like you're mixing the ingredients together, or you're receiving food ingredients, things like that. So you want to do inspections there to make sure the control points, there's no pollution happening, there's no defects happening there. Before a costly operation, so before you paint something really nicely with an expensive paint, you might want to inspect, because once you cover something with paint, it's hard to see defects after that. Before an irreversible operation might be a good idea, because once you do the operation, you can't get the original back, so you might want to do an inspection. Before a covering process that masks defects like packaging, painting, etc. And that is all for part 1. So we didn't do too much in inspection sampling. That's because statistical process control is more useful and practical, and I would say more powerful, which we're going to talk about in the part 2 of the lecture. But there's still areas where you might want to do acceptance sampling. And so it has its uses. Before you do an irreversible operation or you receive a large shipment from the supplier, it might make a lot of sense to do some acceptance sampling. And that is it for part 1.